sharp absorption. So these are things that you can actually, by looking at the spectrum, you get this information. Then what do you do? The molecule jumps from here to here, goes to E equal to 3, let us say. And then what does it do? Does it just stay there? No molecule is ever going to stay upstairs forever. Because that's a situation in which you have put energy into the system. And mind you, as a normal rule, systems are always trying to get to the lowest possible state. They are unstable. So you put a molecule up there, it doesn't want to stay there. It wants to get back to the first opportunity. So you go up there, but then there is a certain probability again for it to come down. And we call that as the probability of emission. You can translate that into time factors. The molecule goes up there and then comes back after a certain period of time. How long it spends up there is what we call as the excited state lifetime. If it spends a very long time over there, what does that mean? I take the molecule, put it up there, and it stays there forever. Let's say it stays there for 2 seconds. 2 seconds is a long time in spectroscopy, mind you. The molecule stays up there for 2 seconds, what does it mean? It means it's reluctant to get down. But it has to get down because the energy is so high. But why is it not getting down? Selection rules. There is something bothering it. Selection rules are preventing it from coming down. You remember we did atomic spectroscopy. And what is the selection rule we said on spin? Delta S must be 0. And you remember we, even in the exam, I gave you a bunch of transitions, and one of which went from singlet to triplet, and you said, no, that's not possible. But let us say by some means, by chemical means, electric discharge means, I take the molecule, atom in hydrogen and push it into a triplet P state. So let's say the hydrogen atom. What's the ground state for the hydrogen atom? Singlet S. A doublet S 1/2. Okay. So if I if I take the hydrogen atom, the hydrogen is not so great. Let's say helium. Helium, what's the ground state? Singlet S. I can have a triplet P for it. So, and we know that singlet S or triplet P is not possible because it's spin forbidden. But supposing by some electric discharge is sent through helium, this is quite possible. I take the helium and put it into a triplet P. I stop the discharge. So the molecules are all sitting in triplet P. Now they have to come down. And what's the state they have to get back to? The singlet S state. That's the ground state. They all want to get back to singlet S. So right now it's in triplet P, it has to get to singlet S. Selection rule prevents it. What do you mean by saying selection rule prevents it? The probability of this transition is very, very small. It simply means that this molecule existed there for a very long period. Eventually it will come down. But because the selection rule prevents it, this atom of helium will actually sit in the triplet state for a very long time before it can come down. Because it's almost like saying I have to jump down, but it can't jump down. Because selection rules are preventing it. We then say that this triplet P state has a very long lifetime. Because the molecule atom can't just come down because the selection rule prevents it. Okay. So then what happens to the lifetime of the triplet P state? Oh, it will be long. You put a molecule in there, the molecule doesn't know where to go. And therefore it will be a very long lived state, very long lifetime. So anytime you hear people say the state is a very long lived state, or the state has a very long lifetime, what do you think they are talking about? They are actually talking about a state which cannot connect itself to the ground state through an allowed transition. That's what it means. So if I am sitting in triplet P and I have to get to singlet S, prevention by selection rule, the state will be very long lived because the molecule of the atom sitting there doesn't even know where to go, and it will take a long time to get back. So if I do this, after a certain time it will come down. And we say that time that elapses between the absorption and emission process, in a way, is referred to as a lifetime. We will see what lifetime is exactly a little later, but you know what it means, or you understand what it means. I put it up there, after a while it jumps back. How long it spends there is my lifetime, is related to my lifetime. But in fluorescence, what happens? It's in solution, right? It's in solution. If it is in solution, what can actually happen is many things. This molecule can jump down and give you the energy. Now, there are other possibilities. While it is trying to jump down, another solvent molecule can collide with it. And when it collides with it, what could it do? It could take away the excess energy. And if excess energy is gone, this law has jumped down. But now, is it going to emit a photon? No. because excess energy has been taken away by the solvent as heat energy. So here's my molecule with the excess energy, waiting to jump, but finding it hard to do so because of selection rules. But when it's trying to make this jump somehow, here comes the solvent molecule, bangs it, takes away the energy, it sort of drops off. The solvent molecule now has got more energy, it starts to move faster. And if it moves faster, what does that really mean? It simply means it got heated up. So excitation, collision, sort of drop as well as become hotter. And this is what we call as a collisional energy transfer, meaning the excited state energy has actually been lost through a collisional process. So the molecule can do many things. It can pick the excess energy, jump back, give me a photon. And if it does that, then I have a fluorescence experiment. It jumps up, gives the energy to the solvent, then it heats up the solvent and comes back without giving me a photon. So all these are possible. If I don't want the collisions to be happening, what should I do? I must do this experiment under conditions in which there are no solvent. I can do that. If there are no solvent, then this fellow goes up, nobody is going to collide with it and take away the energy, and therefore this fellow will stay there forever and eventually come back by giving me a photon. So if I want to force the molecule into giving me a photon, what should I do? Conduct the experiment under conditions in which there are no collisions. And that's something one can always do. But the experiment that you did in fluorescence, what happens? It's a solution. You probably took the fluorescein, you added water, you made it up. There are water molecules going around. Every time you excite a fluorescein molecule, the water can come and collide with it and take away some energy. So what the water actually does, it collides and this molecule jumps here, jumps here, jumps here. So you have excited it to be equal to 3. But what has the solvent molecule actually done to it? They have collided with it, taken away some energy, and a little while later the molecule finds through a series of collisional processes, it has actually come down to be equal to 0. And then maybe it can jump, making a fluorescence emission. And when it does that, what happens? Two things happen. First, how much energy did you put in? So much. A part of it was lost. So whatever you're going to get back certainly must be less than what you gave it in the first place. So that's the reason why in fluorescence you excited a certain wavelength, and where is the emission coming? The emission is always coming to longer wavelengths. It's always coming to lower energies. And you therefore say that the fluorescence emission is redshifted. It's redshifted, and it's also given the name as Stokes shift. What I was told you at that point. In fact, Stokes was the first one who did this experiment by, I think, taking some alcohol, keeping it in a wine glass, shining light from the sunlight, and then seeing what colors came out. And he found that there were a lot of colors that were coming out which were much longer. And therefore, he was the one who first stated the shift to longer wavelengths. And therefore, we call this phenomenon as a Stokes shift. What's the issue of Stokes shift? I put certain energy into the system. The Frank-Condon principle dictates that I go to B equal to 3. From there, the molecule relaxes, comes to B equal to 0, and this flow must come down. Again, the Frank-Condon principle will dictate where you will get down to. Where would I get down to? I can't get down to this side. I have to get down somewhere over here. How do I go from here to here now? Solvent. And will collide from here, I make a jump, and again this process starts. So if you want to look into the system, what will you actually see? An excitation, a collision coming to lower levels, then a fluorescence emission going up to lower levels, another excitation sometime later. So you have collisional de-excitation over here, you have collisional de-excitation over here, and in between you have two fluorescence acts or two photonic acts. Absorption and an emission. And you can see that the emission is going to be of a much smaller energy than the absorption, and that's the reason why we talk about a Stokes shift. So whatever you did in fluorescence experiments, and what was the experiment fluorescence spectrum looking like? That was your excitation spectrum. What are the emission spectrum looking like? Meaning that you have a lot of intensity out here and dropping off. Again, the width tells me It's a progression I'm dealing with. Why would I get a progression? Because this is shifted related to this. I probably will make a transition here, I'll make a transition here, I'll make a transition here. I'll see a whole bunch of levels out here, and the Frank quantum principle again dictates that in the emission, it's quite broad again. Absorption is quite broad again, because the two curves are shifted relative to each other. And that's the reason why you see this. Anytime you do a fluorescence experiment, you see very sharp peaks, you know that the potentials are very similar and laid out one over the other. Anytime you see broad peaks, what you saw in fluorescence experiments, you know that the potentials are basically shifted because the width of the spectrum is so large that you saw. So whatever you did there, you must be in a position to go back and start explaining that on the basis of the Frank quantum principle, which we have been looking at for the last couple of days. And that's basically what I was telling you, that this is used to actually explain observed experimental data. Fluorescence spectrum is observed experimental data. And if you start asking yourself these questions, why is the spectrum broad? Why is the fluorescence coming at the emission spectrum coming in longer wavelengths and shorter wavelengths? At the heart of all this explanation is the Frank quantum principle. The Frank quantum principle is basically the one that will explain to you as to why the spectrum is broad, why one should come in longer than the other, and so on and so on. Okay? Let me introduce one more small concept for the next 5 minutes, and we will stop at this point. And this is something some of you asked earlier. Okay? What does this potential tell me really? Starting from here, I can go to 0, I can go to 1. So I can see a progression, a small progression. The way I have got the potential, if I start from here, I must see progression. Okay. Now, let's see. I have a curve out here, this way. And this curve is a dissociated curve. And this is a bound curve. And what do I mean by a bound curve? What a molecule is there, it will just keep vibrating. It will not break apart as long as you are within that well. If I go out of that well, then of course it breaks apart. But as long as I am within that well, the molecule isn't going to break apart. But what will happen if I get to a state like this? The moment I get out, the molecule is gone. That's a dissociative state. And we saw that in the case of hydrogen, the hydrogen molecule, that you can get a dissociative state. And when we get a dissociative state, when I have electrons in the antibonding orbital as many as I have in the bonding. 0 bond order molecule is broken apart. Supposing I use energy to go, let us say, up to here. Let's say I don't know the state exists. I don't know this. Nobody has told me, nobody has discovered the state. All people know is that there is this state over here, and I am trying to do an experiment with that state. So what do? I go to V equal to 0, I get a spectrum. I go to V equal to 1, I get a spectrum. But I find something weird. When I excite the molecule to V equals 1, suddenly I find the molecule is breaking apart. It's gone. But going to V equal to 1, the molecule shouldn't be breaking apart, because it is sitting within the bed. Where is the dissociation limit coming? Here. If I go above this, then it can break apart. But if I am going inside here, it cannot break apart. Therefore, I feel there is something really going on. I have actually excited the molecule to an excited state, but within the potential web, you don't expect the molecule to break apart, but you find the molecule actually is breaking apart. This is seen very often in spectroscopy. And then you suddenly realize that this can happen provided I have a state that's doing this. And that state, mind you, is crossing this right here. Now what do you think will happen? I excite the molecule to this level. Molecule is now sitting at B equal to 1. When it sits in B equal to 1, what will it do? It will start to vibrate. And when it vibrates, what will happen to it? It will increase and get here. At this point, the molecule faces a dilemma. It does not know whether it belongs to this potential or the other potential because both potentials are crossing each other. Therefore, the molecule does not even know whether it is sitting on the bound potential or whether it is sitting on the repulsive potential. Part of the molecule might think it is actually sitting on the repulsive potential, and therefore it will actually jump from this potential into this potential. And if it jumps to this potential, what's its fate? Gone. It's gone. The molecule breaks apart. And this is what we call as pre-dissociation. Why is it called pre-dissociation? Because it dissociates ahead of time. Meaning, I really expected that molecule to dissociate only after I gave it this much of energy. But somehow it seems to be dissociating at an energy that is much lower than the limit I require to get to. And this is therefore called pre-dissociation. And when will pre-dissociation occur? Pre-dissociation will occur if this state actually crosses a repulsive state. And if this vibration level and this vibration level and this potential here cross over it. What's the nice thing on this point here? How do we explain this? What about supposing I go to B equal to 2 state? Will the molecule undergo pre-dissociation? That's the question. Will the molecule undergo pre-dissociation? Well, you don't know that, right? Because it is crossing this level over here. It's crossing that vibration level over there. So as the molecule is traversing that point, what should it do? It should be in a dilemma, and then it could jump. Go back to the